Look at whatever screen you are near right now, or, if you have a book open, just glance down at the page. Find the period at the end of a sentence.
Just a tiny speck.
Right, exactly.
Right.
Just stare at how tiny that dot is for a second. Now, I want you to imagine a time when absolutely everything in existence, and I mean literally everything, was squished into something smaller than that little speck of ink.
Yeah, it is. Honestly, it's almost impossible for the human brain to truly picture.
Mm.
But to understand how our universe works,
Yeah.
that is exactly where we have to begin.
Absolutely. So welcome back. You are listening to part 2 of our 20-part deep dive series. We are dedicated to helping you completely crush the New York Regents science exam.
And if you're an honors middle schooler staring down that test, just take a deep breath. You've got this.
Yeah, we are tossing the flashcards aside today. We're not just going to memorize a dense review sheet, right? We are treating this material like the ultimate cosmic detective story. And today's case as well, it's the biggest origin story of them all, the Big Bang Theory.
Which is great because science is essentially just solving mysteries using evidence. And your review sheet is absolutely packed with the clues.
So true.
Our goal today is to connect those clues so you understand the mechanisms, the how and the why behind the universe. Because when you understand the story, the vocabulary terms just naturally fall into place.
Okay, let's unpack this because my brain is still kind of stuck on that tiny dot. We are going back 13.8 billion years, right?
13.8 billion.
I want you, the listener, to try to build this in your mind. Think about everything in the universe, not just your room or the Earth, like every planet, every star, all the billions of galaxies out there.
Your dog, your science textbook,
Yeah.
all of it.
See, it's all that matter and all the energy that has ever existed, and compress it. Shrink it down until it is an incredibly small, infinitely dense point. That dot is what physicists call the singularity.
And what's fascinating here is that when you compress that much stuff into a space that's infinitely small,
Yeah.
the rules of reality itself just, well, they shatter
They just break.
completely. Your test materials mention a very important concept called general relativity.
Right, Einstein's famous theory. We usually think of that as, like, the ultimate rule book for how gravity works.
It is. It's the rule book for how massive objects curve space and time. But here's the problem. In a singularity, you have all the mass of the universe occupying zero volume.
Oh, wow. Zero volume.
Exactly. So if you try to calculate the density of that, you are mathematically dividing by zero.
Which you can't do. My math teacher would definitely fail me for that.
Right. The curve in space becomes infinitely steep. It's a bottomless pit where our equations literally just output the word infinity. And in physics, when your math gives you infinity, it means your theory is broken down.
So it just stops working.
Yeah. The normal laws of physics simply did not apply inside that dot.
So gravity, time, space, they didn't exist in any way that makes sense to us. It was just pure, raw, incomprehensible potential.
Which means we can't really look before the singularity because time itself didn't exist yet. It is the absolute starting line.
Wow. Okay, so let's lock this in for test day. When you see a question about the singularity, you have 3 key checkpoints. 1, it existed roughly 13.8 billion years ago.
Right.
2, it contained all the matter and energy that exists today. And 3, the current laws of physics were completely broken inside it.
Spot on. And because those laws were broken and the pressure was infinitely high, it couldn't remain a tiny dot.
It had to go somewhere.
It had to break out. Which brings us to the event itself.
Here's where it gets really interesting, because the name Big Bang is honestly terrible branding.
Oh, it's the worst.
Right. When people hear bang, they picture a firecracker or maybe a bomb going off inside an empty room.
And that is probably the most common misconception. The Big Bang was not an explosion in space. There was no empty room for it to explode into.
Wait, really?
Yeah, the Big Bang was an explosion of child space.
Okay, I was originally going to use an analogy about opening a hot oven and letting the heat expand into a kitchen, but based on what you just said, that doesn't work because the kitchen already exists.
Exactly. You can't expand into something that isn't there yet.
So how do we actually visualize an explosion of space?
Okay, imagine you have a completely deflated balloon, take a marker, and draw a bunch of little dots all over the rubber. Those dots represent galaxies.
Okay, I'm picturing it. Deflated balloon covered in dots.
Now, start blowing up the balloon. As the rubber stretches, the dots move further apart from each other.
Oh, I see. The dots aren't sliding across the surface of the balloon. The surface itself, like the space between them, is getting bigger.
Precisely. That is the rapid expansion of the Big Bang. Space itself began stretching outward at an unimaginable speed. carrying all that raw, blazing energy with it.
And as it expanded, a critical change happened. According to the review material, the universe began to cool down. But wait, I have a logical pushback here.
Let's hear it.
How does an entire universe cool down? I mean, space is already a vacuum. It's not like you can just turn on a giant air conditioner.
That is a great point. To understand that, we have to look at what temperature actually is on a microscopic level. Temperature is just a measurement of how fast particles are vibrating or moving.
Okay, so the faster things bounce around, the hotter it is.
Exactly. In the first few fractions of a second after the Big Bang, the universe was violently hot. We're talking billions of degrees Celsius. It was just a dense, glowing soup of pure energy.
Because all that energy was crammed together, so the particles were vibrating so wildly, slamming into each other at such extreme speeds that they couldn't possibly stick together.
They were moving way too fast for any cosmic glue to hold them. But as the universe rapidly expanded, as that balloon inflated, the energy spread out over a much larger volume.
Oh, right. And as energy spreads out, the overall kinetic energy, or temperature, drops.
Exactly. Things started to slow down.
And this cooling process is basically the master builder of our universe, because once things slow down, they can finally connect, right?
That is the magic mechanism right there. As the temperature dropped, that soup of pure energy condensed into the very first subatomic particles. We are talking about protons, neutrons, and electrons.
But even then, they didn't form atoms immediately, did they? Because they were still moving pretty fast. I'd imagine an electron trying to orbit a proton would just smash right through it.
Yeah, it took hundreds of thousands of years of continuous expansion and cooling.
Mm.
Finally, the universe cooled enough that these subatomic particles slowed down to a manageable speed.
And that's when things finally clicked.
Yep. The strong nuclear force and electromagnetism could finally grab hold. The subatomic particles locked together, forming the very first, simplest atoms.
So for the Regents exam listener, this is a crucial chain reaction to memorize. You need to know the why behind the what.
Definitely. Cause and effect.
Right. Expansion causes the energy to spread out. That spreading causes cooling, which is just particles slowing down. Slowing down allows subatomic particles to form and stick together. And those locked together particles form the first atoms.
It is an incredibly elegant sequence.
Expansion, cooling, subatomic particles, atoms, boom.
But, it does bring up a major problem for our detective story.
Oh, right. We are detectives. We are building this case for an event that happened 13.8 billion years ago, but there were no witnesses, no cameras.
Not a single one.
We just spent all this time talking about singularities and expanding balloons and cooling protons. How do scientists actually any of this is true? Because science requires hard physical evidence.
It does. And if we connect this to the bigger picture, the universe actually left us a fingerprint. 2 fingerprints, actually. And they are both heavily featured on your exam prep.
Awesome. Let's tackle the first one. The cosmic microwave background radiation, or CMB.
Right.
Oh, cosmic microwave background. That sounds incredibly technical.
It does sound intimidating, but let's break it down using our detective narrative. Remember that for the first few 100,000 years, the universe was incredibly hot and dense. It was basically a glowing, opaque fog of plasma.
So you couldn't see through it. No, light couldn't travel anywhere because it kept bouncing off all those loose, high-speed particles.
Oh, I get it. It was like trying to drive through a thick blizzard with your high beams on. The light just scatters everywhere.
That's a perfect analogy. But then the universe expanded and cooled enough for those first atoms to form. When the electrons finally locked onto the protons, the fog instantly lifted.
Space became transparent.
Exactly. And for the very first time, all that trapped light was able to shoot freely across the universe in every direction.
A massive cosmic flash of light.
And that first flash of light has been traveling through space for over 13 billion years. But remember, space is still expanding.
Right. The balloon is still inflating.
So as space stretched, those original light waves got stretched out too. They stretched from highly energetic visible light all the way down to low-energy microwaves.
Oh. And today, we can still detect those stretched out microwaves everywhere we look in the sky.
Everywhere. It is literally the leftover heat, the afterglow of the Big Bang itself.
Okay, listener, here is an incredible fact about the CMB that makes it impossible to forget. Have you ever seen an old school, bulky analog television set, like the ones with the antennas?
Oh yeah, the really heavy ones.
Yeah. When you turn them to a channel that didn't exist, the screen would just show fuzzy black and white static, and you'd hear that loud hissing noise. Well, a small percentage of that static, about 1% of it, was actually the television's antenna picking up the cosmic microwave background radiation.
That's wild to think about.
You were literally watching the leftover heat of the Big Bang right there in your living room.
It is one of the greatest accidental discoveries in science history, actually. Back in the 1960s, two scientists named Arno Penzias and Robert Wilson were using a giant microwave antenna for radio astronomy.
Okay.
And they kept picking up this constant, annoying background hiss no matter where they pointed the antenna. They were so confused they even climbed inside the massive horn and scrubbed out a bunch of pigeon droppings, thinking the bird poop was causing the interference.
Wait. They thought the greatest piece of evidence for the origin of the universe was pigeon poop.
They really did. They spent hours cleaning it out. But the hiss never went away because it wasn't birds. It was the echo of creation. The CMB proves that the universe was once infinitely hot and dense everywhere all at once.
Okay, that is hilarious. So CMB equals leftover heat and radiation from the Big Bang. That is a massive clue for our cosmic detective case. So what does this all mean for the second piece of evidence? It's called redshift.
Redshift.
How does that prove the universe is expanding?
To understand redshift, we have to talk about the Doppler effect.
Okay, listener, you have definitely experienced the Doppler effect in real life. Imagine you are standing on the sidewalk and a police car speeds past you with its siren blaring. Think about how the pitch of that siren changes.
Right, the sound changes depending on where the car is.
Exactly. As the car is driving toward you, the sound waves get bunched up and squished together in front of the car so the pitch sounds really high, like wee 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 woo.
Great sound effects.
Thank you. But the exact second the car passes you and starts driving away, the sound waves trail behind it and get stretched out. The pitch drops and sounds deeper. Wah, wah, wah.
That stretching of the wave is the key. Sound travels in waves, and so does light.
And different colors of light have different wave sizes, right?
Exactly. On the visible spectrum, blue light has very short compressed waves. Red light has very long, stretched out waves. So let's go back to our balloon analogy. The galaxies are the dots on the balloon.
Okay.
As the balloon inflates, the space between the galaxies stretches.
So if a distant galaxy is shining its light toward us and the space between us is physically stretching like rubber,
Yes.
then the light wave itself has to get stretched out as it travels through that space.
You've nailed it. When astronomers look through telescopes at almost every distant galaxy in the sky, they see that the light coming from them is shifted toward the red end of the spectrum. The light waves are physically longer than they should be.
Because just like the ambulance siren stretching out its sound waves as it drives away, the galaxies are stretching out their light waves as they move away from us.
The redshift is the ultimate proof that the galaxies are moving apart. And if everything is moving apart right now, well, then logic dictates that if you rewind the clock 13.8 billion years, everything must have been packed together in a single point.
This is an absolute must-know for the Regents. When a test question asks about redshift, your brain should immediately yell expansion or galaxies moving away. Redshift means the universe is stretching.
Absolutely.
And when a question asks about the cosmic microwave background, or CMB, your brain should immediately yell, leftover radiation from the Big Bang. These are the two smoking guns.
Match those concepts to their mechanisms, and you will ace that section of the exam.
All right, our detective story is looking pretty solid. We started at a singularity, we expanded, we cooled subatomic particles locked into atoms, and we proved it with redshift and the CMB. But we actually have a glaring plot hole.
A plot hole.
Yeah. According to the timeline we just built, the Big Bang cooling process gave us atoms, but it only gave us two specific types of atoms, hydrogen and helium, with maybe a tiny trace amount of lithium.
That is correct. Hydrogen, which is just one proton, and helium, which is two protons. They are the absolutely lightest, simplest elements in the universe.
But look around. Look at the Earth. Look at us. We are breathing oxygen. Our cells are built entirely on carbon structures.
Yeah.
The core of our planet is made of heavy iron. There is gold, silver, uranium. The periodic table is huge.
It really is.
If the Big Bang was just a giant box of basic hydrogen and helium, how did we build an incredibly complex universe? It's like trying to build the Eiffel Tower, but someone only handed you like a box of basic single-peg, one-by-one Lego bricks.
Right.
Where did all the complex multi-peg pieces come from?
This raises an important question, and it introduces the final major phase of our origin story. The Big Bang provided the raw, basic building blocks, your one-by-one Lego bricks. But to forge heavy, complex elements, the universe needed specialized factories. It needed massive pressure cookers. And those factories are the stars.
Wait, stars make the elements? I thought they just burn gas to make light.
They do produce light, but that light is a byproduct of the incredible manufacturing happening in their cores. Let's look to mechanics. If you want to make a heavier element out of light elements, you have to smash their nuclei together.
Okay, so you have to force positively charged protons to bond.
Exactly.
But protons are positively charged. If you try to push two positive charges together, they repel each other. It's like trying to force the north poles of two strong magnets together. They constantly push back.
That's very true.
Yeah.
To overcome that extreme magnetic repulsion, you need an overwhelming, terrifying amount of force. Deep inside a massive star, the gravity is unimaginably strong.
So it just squeezes everything.
Right. The crushing weight of the star squeezing inward generates insane heat and pressure. Enough pressure to overpower that magnetic repulsion and literally crush hydrogen and helium atoms together.
Fusing them into heavier things.
Yes. This process is called nuclear fusion. The star acts as a giant forge, taking light atoms and fusing them into carbon, then oxygen, then silicon, all the way up to iron.
Nuclear fusion. So on the exam, listener, fusion means taking light elements and crushing them together inside a star to build heavier elements.
Exactly.
But wait, if the star is doing all this heavy lifting deep inside its core, those elements are trapped, how does the carbon get out of the star and into my DNA?
Well, it requires a spectacular delivery mechanism. A violent death.
Oh, dramatic.
Very. A star is basically engaged in a massive tug of war for its entire life. Gravity is constantly trying to crush the star inward, while the energy from nuclear fusion is pushing outward, keeping the star inflated.
But eventually the star has to run out of fuel to fuse, right?
And when it does, the outward push stops. Gravity instantly wins the tug of war. The entire weight of the star collapses inward at thousands of miles per second.
Whoa.
This collapse creates a shockwave so powerful that the star rebounds and blows itself to pieces in one of the most violent events in the cosmos, a supernova.
The star just annihilates itself.
The explosion is so intensely hot and powerful that in those final few seconds, the supernova creates enough energy to fuse the extremely heavy elements, things like gold and uranium.
That's incredible.
And then it blasts all those elements, the carbon, the oxygen, the iron, the gold, out into interstellar space.
It just scatters the complex Lego pieces across the galaxy.
Exactly. And over billions of years, those drifting clouds of heavy elements begin to clump together. Gravity pulls them into rocks, asteroids, and eventually planets.
So the Earth is literally just a clump of debris from a detonated star.
Which means you are made of that same debris. The iron carrying oxygen through your blood, the calcium making up your teeth and bones, the carbon in your skin. Every single heavy atom inside of you was forged in the belly of a dying star that exploded billions of years ago.
That is just wow.
You are quite literally walking, talking stardust.
Okay, that is profound. But let's make sure it is profoundly useful for your test score. You must keep the elemental timeline straight.
Good call.
If a Regents question asks what the Big Bang created, the answer is only the lightweight stuff, hydrogen and helium. If the question asks where the heavier elements come from, the answer is stars.
Right. They are created through nuclear fusion, and they're distributed by supernovas.
Big Bang equals hydrogen and helium. Stars equal everything heavier.
That perfectly summarizes the chemistry and evolution of the early universe.
And just like that, we have cracked the case on this incredibly dense review sheet. Let's do a rapid-fire recap to lock the narrative into your brain.
Let's do it.
We started 13.8 billion years ago with a singularity, a dot of infinite density where all the laws of physics were broken. It rapidly expanded, stretching space itself like a balloon.
And as space expanded, the kinetic energy spread out, which caused the universe to cool down. This cooling allowed particles to slow down enough to form subatomic particles, which then bonded into the first basic atoms of hydrogen and helium.
We know this happened because we have the evidence. We can literally see distant galaxies moving away from us because the space between us is stretching their light into longer waves. That is the redshift.
And we can detect the leftover heat of that original rapid expansion lingering in the background of the sky. That is the cosmic microwave background radiation.
Finally, we learned that those basic hydrogen and helium atoms were pulled together by gravity to form stars. Through the intense heat and pressure of nuclear fusion, stars crushed those light elements into all the heavy, complex elements we see today,
Blasting them into space through massive supernova explosions.
You now know the entire story. from the dot to the stardust. When you sit down for the Regents exam, you aren't just going to be reciting rote definitions. You understand the how and the why. You know exactly how the pieces fit together.
You are going to do incredibly well. But before we sign off, I actually want to leave you with one final mind-bending thought to ponder on your own. It builds directly on the mechanics of redshift.
Oh, bring it on. I love these.
We know from redshift that the universe is constantly expanding. The space between galaxies is stretching, pushing them further and further apart. But astronomers have recently discovered that this expansion isn't slowing down. It is actually accelerating.
Wait, it's speeding up.
It is speeding up. So if you fast forward the clock, think about what the night sky will look like billions of years from now. As the space between us stretches faster and faster, will those distant galaxies eventually be pushed so far away and their light stretched so thin that they simply vanish from view?
Oh my gosh.
Will future stargazers look up at the night sky and see nothing but an empty, pitch-black void, completely unaware that a massive universe is even out there?
Wow. They would look up, see blackness, and think they were entirely alone in the universe, because the evidence simply sped away from them.
Just something to think about.
That is a wild, chilling thought to leave you with as you hit the books. Thank you for joining us for part 2 of our Regents Prep Deep Dive. Keep trusting the process, keep tracing the clues, and we will see you right back here for part 3.
Where we are jumping out of the distant past and diving straight into the mechanics of our very own solar system.
Until then, stay curious.